let us start with the shear plane. So, concept of shear plane. What is shear plane? The plane along which the workpiece shears or cracks is called as the shear plane, or it is simply the plane which separates the chips from the workpiece is known as the shear plane. Now, if you look at the diagram, see, this is the workpiece, this is tool, and this is chip. You know very well. Now, this region is our shear zone. This is the shear zone, and the shear zone is extending to a very narrow region, and it is represented by a very thin straight line. This is one of the assumptions of Merchant theory. This thin straight line is our shear plane. So the plane along which the workpiece is shearing is known as the shear plane, or the plane which separating. You can see here the plane is separating this cut chip from the workpiece, or the cut chip from the uncut chip or undeformed chip, right? So this is the shear plane. And the second very important thing we have to keep in mind, that the volume constancy principle is valid for the metal cutting also. So when the force is applied by the tip of the tool along the lengthwise direction in a layer of this workpiece material, the huge compressive stresses are produced in front of this tip of the tool, and because of that, along the lengthwise direction, the volume reduction is there. So as the volume is reducing along the lengthwise direction, it has to increase somewhere else. So it will increase either in width direction of the chip or in thickness direction of the chip. But the width of the chip is more or larger than the thickness of the chip, the material will flow along the thickness direction. That's why this chip is become thicker and thicker. This is the outward flow of material, yes or no? That is the cut chip thickness. This T1 is undeformed or uncut chip, which is still present inside the workpiece. This is the cut chip from the workpiece. So thickness of this cut chip, that is T2, is always greater than T1. That is the thing. See here. See, outward flow of the metal causes the chip to be thicker after separating from the parent material. The reason I explained just now. That is, the produced chip is thicker than the depth of cut. So let us see here. T1 is our uncut chip thickness. T2 is our cut chip thickness. The ratio of these two, that is T1 by T2, is known as the chip thickness ratio. Please remember, very important, this R, small r, is our chip thickness ratio. What is the value of R? This uncut chip thickness divided by cut chip thickness, that is T1 by T2, is our chip thickness ratio. Obviously, T2 is bigger than T1, then this ratio R is less than 1. And if we have the reciprocal of this ratio R, chip thickness ratio R, that is 1 upon R, is known as the chip reduction coefficient. And this chip reduction coefficient is represented by the letter Greek symbol zeta, which is equal to 1 upon R, or T2 divided by T1. As T2 is bigger than T1, this chip thickness or chip reduction coefficient is more than 1. Okay, so let us go for the expression for the shear plane angle. So as the definition of shear plane, we know the shear plane. Now what is the shear plane angle? And it is represented by letter phi. So friends, look at the diagram here. Now I have given the names for various things here. Now see our shear plane, this OA, you can see here this OA is our shear plane. Okay, and this T1 is our uncut chip thickness, T2 is our cut chip thickness, and you can see here the symbol phi, which is representing the angle OAB. And yes, this OAB is our shear plane angle phi. So what is definition of shear plane angle? So this angle made between this shear plane and this cutting velocity vector VC is known as the shear plane angle phi. Very simple. So here the cutting velocity vector VC is going in this direction, and this OA is shear plane. Between these two, the angle is made is our shear plane angle. Okay. So before going in details about the shear plane angle, let us have some basic things. Just now I discussed that as the volume constancy is valid, that the width of the chip is not going to change because the flow of the material is not along the widthwise direction. It is flowing in a thickness direction. That is why the width of the chip, that is represented by small b, remains unchanged. Please remember this. Width of the chip remains constant. Now, if I have the original length of the chip is LO, then length of the cut chip is LC, cut length of the chip or final length of the chip is LC. We know T1 and T2. As I told you that volume constancy principle is valid, then of course we can write volume before cutting is volume after cutting. That is area into length is volume. This A original into L original is the original volume, should be equal to final volume, that is A final into L final, or L final here was the length of the cut chip, that is you can write LC also here, right? So see, volume constancy, what is initial area or original area? This thickness into T1, okay, T1 into this width of the chip into L original equal to B2 into T2 into L final or LC. But you know width will be remains same. This B1 B2 gets cancels, then we get T1 divided by T2, which is equal to L final divided by LC. Yes or no? T1 divided by T2 is L final divided by L original, that is LC divided by LO. Or simply if we equate these in terms of the volume flow rate, this instead of simply volume in terms of volume flow rate, then there will be the three velocity actually we are getting. Along the cutting direction we are having the cutting velocity, along the shear plane we are having the shear velocity, and where chip is flowing we are getting the chip velocity or simply flow velocity. In terms of these velocities, if I have the volume constancy, I can write this b1 t1 into cutting velocity, the velocity with which we are cutting, relative velocity with the workpiece, equal to the outward volume flow rate, which is the chip is flowing with, b2 into t2 into vf. Vf is the chip velocity of flow velocity. So here also we can get this b1 b2 get cancels, and we will get t1 by t2 is equal to vf divided by vc. This is also the chip thickness ratio r. Okay, so now we have got the relation for this chip thickness ratio, that is it can be either represented by t1 by t2, or it can be represented by chip length, cut length divided by original length, or also we can now represent this r by the flow velocity. See here, this is the flow velocity divided by this cutting velocity. As I mentioned here, there are three velocities. One is the cutting direction VC along the shear plane. This is VS, shear velocity, and this chip is C is moving on the rake face. This is C. This is known as the rake face of the tool. The chip is sliding or moving over a rake face of the tool with the flow velocity Vf. So we can write this R as T1 by T2 or LC by LO or Vf by Vc. Now look at the diagram. What we can have here, please, what I did here. So from the point O, I have drawn a normal on the this rake face of the tool at point C. Okay, this T1 is your uncut chip thickness. So please look at the geometry and understand, if this is a phi, this angle, this is, we know this is a rake angle always, the angle between the rake face and this line. Okay, so basically this is the slope along the longitudinal direction on the rake face of the tool. Okay, so this is a rake angle alpha. So we know that this OA is our shear plane LS. Now the shear plane will be represented by small letter L S, and this is our cut chip thickness T2. Now if this angle here is alpha, that is a right angle, then triangle angle AOC will be what? Phi minus alpha. Please check the geometry. This is phi, this OAB is shear angle phi, this OCA is 90 degree because OC is normal on this face. Then, and this dotted line with the rake face having angle alpha, this alpha, then this angle will be this 90 minus phi, and total angle will be OAC will be 90 minus phi plus alpha, this angle OAC. And if we minus it from 180 degree, you will get this phi minus alpha. AOC will get phi minus alpha. Okay, so please see carefully. So here now, if in triangle OAB, if I write for the sine of angle phi, then I can write this will be equal to OB divided by OA. Yes or no? See, where OA, I told you that is the length of the shear plane, which is LS. And you know OB is our uncut chip thickness, isn't it? So we can write this sine of angle phi is equal to this T1 divided by LS, or I can write LS is equal to T1 divided by sine phi. Simple thing. In same fashion, if I see the triangle OAC, in triangle OAC, what is the cos of angle phi minus alpha? The cos is nothing but the adjacent divided by hypotenuse. Adjacent is again OC and hypotenuse is OA. So OC divided by OA. So again we can write OC is what? Our cut chip thickness T2, and OA is here. Please correct here. OA is our the shear plane LS, and OC is our cut chip thickness T2. So cos of phi minus alpha, we can write it as T2 divided by LS. Or again, if I want to write for LS, then LS will be T2 divided by cos of phi minus alpha. This is equation number A, and this is equation number B for same shear plane length. So definitely we can equate this A and B, and we will get T1 by sin phi is equal to T2 by cos of phi minus alpha. So you can write in the form of T1 by T2 is equal to sine of phi divided by cos of phi minus alpha. You know T1 by T2 is our chip thickness ratio R. Then if I write it as 1 upon R is equal to cos of phi minus alpha divided by sin phi. And we know that what is cos of A minus B? cos A cos B plus sin A sin B. We can write it as 1 upon r is equal to cos phi into cos alpha plus sin phi into sin alpha divided by sin of phi. See here, simple mathematics. So cos phi divided by sin phi is a cot phi. This into cos alpha plus sin phi get cancels here, remains only sin alpha here. So after simplification, you will get here this tan of phi is equal to r cos alpha divided by 1 minus r sin alpha, or phi is equal to tan inverse of r cos alpha divided by 1 minus r sin alpha. So that is very important relation. See, this is very important relation, that is calculation of shear angle. So shear angle phi can be calculated as, it is a tan inverse of r into cos of rake angle alpha divided 1 minus r into sine of rake angle alpha. Please remember, this r is, we know, chip thickness ratio r, alpha is our rake angle. Okay, so this is the expression for the shear angle phi. Now with this, we can also have the relationship between the three velocities that we already know. Please remember which are the three velocities. The velocity along the cutting, it is cutting velocity Vc. Along the shear plane, the velocity, shear velocity Vs, and chip is flowing with the chip velocity or flow velocity Vf. Now with this information, now I am having the rake angle this alpha, I am having this shear angle phi. Now see here, if I draw here the triangles for the velocity and shear velocity and the flow velocity. So this is the cutting velocity C, this is cutting velocity Vc. With angle phi, we are getting along this shear plane, this velocity is Vs, and this is flow velocity. See, this is the flow velocity, and this here, this is the tip of the tool here, this is the tip of the tool here. So this angle is alpha, so definitely this will be 90 minus alpha. We know this is a shear angle phi, then this will be 180 minus these two angles will be 90 minus phi minus alpha. This is very simple. See, this is the velocity triangle, right? Now from this velocity triangle, if I apply the sine rule, what I can write here? See, I can write this sine phi, or this flow velocity divided by this sine phi, yes, is equal to this shear velocity divided by sine of 90 minus alpha, or this equal to this cutting velocity divided by the sine of phi minus alpha, 90 minus phi minus alpha. So by the sine rule, I can write, see, Vc divided by sine of 90 minus phi minus alpha equal to Vs divided by sine of 90 minus alpha is equal to Vf divided by sine of phi. So on simplification, that is sine 90 minus theta is cos theta. I can write here the velocity relationship as Vc divided by cos of phi minus alpha equals to Vs divided by cos of alpha equals to Vf divided by sine of shear angle phi. Vc cutting velocity, Vs shear velocity, Vf flow velocity of chip. Phi is the shear angle, alpha is the rake angle. Please remember this. This is the relationship between the velocities. And once again, it is very much clear that we can write for Vf divided by Vc, it is nothing but sine of phi divided by cos of phi minus alpha, which is also our chip thickness ratio. So in shear plane angle, we also got this equation, that is r is equal to sine phi divided by cos phi minus alpha. We got the reciprocal of 1 upon r is equal to cos of phi minus alpha divided by sine phi, and we express the relation for the shear angle phi. Okay, thank you.